Okay, I'm going to start with number 26. Why is Mount Kilimanjaro covered in snow throughout the year, even though it's on the equator? The answer is elevation. Elevation or altitude. The higher up it gets, the colder it gets. And really that's because there's less air, so there's less conduction of heat. 27. Why does a coastal town tend to have warmer winters? Okay. The short answer is proximity to water, but let's fully explain that. Why would it have warmer winters? Well, let's start in the summer. By the late summer, the water has finally heated up. You wouldn't want to go swimming in May. You might want to go to the beach in May, but you wouldn't want to go swimming in May. So let's say July, August, the ocean's finally pretty warm. Well, around September, October, November, the land is going to start to cool down really fast. We know that rocks and soil have a very low specific heat capacity, so they cool down fast. Water retains its heat very long. It has a very high specific heat capacity. So in the early winter months, the land gets really cold really fast, but the water still holds so much of its heat from the last summer. So that heat slowly releases into those coastal communities, and that's why they tend to have warmer winters. 28. Why does it have cooler summers? Well, let's just continue in our talk. So I said it has warmer winters, and let's say February or January, February rolls around. By now, the ocean has finally lost all of that stored up heat, and it's now very cold. Well, March, April, May come along, and the sun is more direct now. It heats up the land very quickly, and it's shining down on the ocean, but it heats up the ocean very slowly. Again, it's because of water's high specific heat. Water heats up very slowly. So by the time May rolls around, the land is pretty warm, but the ocean is still very cold from the winter. Okay, so that's why going into the summer, it's going to still be very cold. Colder near a coastal town. So even in June and July, the land is very hot, but the ocean is still a little bit cold from the last winter, and some of that heat from the coastal towns kind of go into the ocean and cool the coastal town down a little bit. 29. Name 4 climate proxies. For each one, give a short explanation. First one we talked about was tree rings. And the simple answer for this is a thicker tree ring means a tree grew more during that year, and that can be attributed to warmer time periods. A very thin ring means a tree barely grew that year, so that's probably indicates that it was cold that year. Next climate proxy we talked about was pollen. With pollen, you look inside a sample of dirt. This is going to be the top. This is the bottom. So this is the new stuff, and that's the oldest stuff. And let's say you find pollen from all in here, and let's say this is certain pine trees and coniferous trees and things like that. Well, that probably tells you it was cold here. And if at the top you find like deciduous trees like open oak and maple, and if you find tall grasses, well, that probably means it was warm. So you look at the type of pollen seeds that you see, you look at what climates those can grow in, and that tells you what the climate was like. Third proxy we could talk about is 018 versus 016. This one's a little tricky. Still in number 29. 018 versus 016. These are two isotopes, which by now you guys know all about. This one's heavier. Obviously, this one's lighter. So let's say you're a scientist and you're looking in Greenland or Antarctica ice cores, and you find a lot of 018. Well, in order to get there, this 018 must have left the oceans, flown in the air all the way to the North Pole or the South Pole, and then landed and got trapped or deposited or rained, snowed onto the glacier. So in order for that to have gotten there, it must have been pretty warm, because the heavier stuff can't really leave the ocean unless it's warm enough for it. Okay? So if you're up there and you find very little 016, well, if you find very little 018 and a lot of 016, it was probably cold. If you look at the bottom of the ocean, though, that's different. Let's say you're now looking at a deep sea core sediment. Well, if you find a lot of 018 down in the bottom of the ocean, what that tells you is that the 018 wasn't able to escape, and instead it was left behind. So therefore, it was probably cold. Okay, so that's your indicator there. If you find very little O18, and again, it's easier to look at it from the O18 perspective from more of it, but if you find very little O18 and a lot of O16, it's a good indicator that it was probably warm because that O18 was able to escape out of the ocean. Okay, still on 29, still talking about climate proxies. One more we talked about was CO2 or other greenhouse gases trapped inside bubbles inside ice cores. So we've dug ice cores that are almost a mile long in Greenland. If they look down inside bubbles and they find a lot of CO2 in a particular area, they know it was very warm there because those are greenhouse gases. Same thing with methane and water vapor, gases like that. If you find a lot of greenhouse gases, it was probably warm. Number 30. Think back to the heating up rocks / soil versus water lab. What was the independent variable? That was the type of surface. So water or rocks or soil. What was the dependent variable? That was the temperature after a certain number of minutes. What were some CVs, controlled variables? Things like the same light bulb, same wattage of light, same distance from the cup, same amount of time, same starting temperature, same overall conditions around it. You don't use Mylar under one and black paper under the other. Number 31. I walk outside on a clear sunny day in December. Why is it so much colder than when I walk outside in June? Well, in December, here's the sun, here's the earth, and the sun's rays are coming like this. Okay? So if you kind of extrapolate these all the way, these three rays are covering that entire surface. Let's do the same thing, but now in June, the sun is coming down around 78 degrees. Certainly not straight down. If you were either in the tropics or the equator, you could get direct sunlight. But for Wilton, it's going to be down like this. So that's our sunlight now. That's around 78. And you notice that all this sunlight, same 3 pieces of sunlight, 3 units of sunlight, they cover only this small area. So it's like if you're sharing. Well, if this sunlight is shared between all of this distance, you can see that it's going to be colder than this, where those same 3 rays of sunlight are shared in just that small distance. So this is the concept of light intensity. When light is more direct, there's more heat per given area, and it's going to be warm. So this is our summer, this is our winter. 32. What's the tilt of the Earth? It is 27.5 degrees. Let me just double check that online if I can here. I believe that's true, but 27.5, let's see, tilt of the Earth. I have all these numbers running through my head. Wow, I was wrong. Good thing I checked. 23.5. 23.5. Okay, so that means this would be straight up, but instead the Earth is more like this. Okay, slight little tilt. Why is this important? Well, the tilt of the Earth is what gives us seasons. If the Earth were like this, there would be no seasons because the middle of the Earth would receive direct sunlight all the time. So basically the whole middle of the Earth would just be a barren wasteland, way too hot to support any life. And the tops of the Earth would never receive any kind of direct sunlight, so it would be super cold and just covered in ice all the time. But instead, because of the angle and because this moves around the sun like this, different parts of the Earth receive direct sunlight at different times of the year, and that's what gives us our seasons. 33. Okay, this is our Sun-Earth relationship drawing. So here's my sun, and let's draw our Earth. So you want to draw the axis, you want to draw the equator, and you want to keep that axis the same way. Okay. So remember, the axis always has to run perpendicular to the equator. I should say the equator should run perpendicular to the axis. Don't accidentally draw this straight across. So I'm going to do the same thing over here, same thing up here, same thing over here. Okay, so that's our basic position. Now let's look at where the direct sunlight's hitting. Well, when it's over here, it's striking down here. Now that's going to be at 23.5 degrees south. That's the Tropic of Capricorn. So this is going to be what we call winter. So this is going to be December. December 20th through 21st. And again, direct sunlight's at the Tropic of Capricorn. If you look over here, direct sunlight is now in the northern hemisphere. So this is what we call summer. So this is going to be June 20th through 21st. And it's hitting the Tropic of Cancer, 23.5 degrees north. And on these 2 days, it's going to be halfway in between. So it's going to hit the equator both times. Remember that, well, if it's 23 south down here, and then in 6 months it's going to be 23 north up here, well, halfway between there is definitely going to be 0. By the way, you have to pick a direction for this to move. You could kind of do it either way, but I do believe the Earth does move around counterclockwise like this. So up here, direct sunlight's going to be hitting the equator. Down here, direct sunlight's going to be hitting the equator. So this is called the winter solstice. This is the summer solstice. This one is going to be, let's see, December into June. So that's going to be March 20 through 21st, and that's going to be the spring or vernal equinox. And then down here is going to be September 20 through 21, and that's going to be your autumnal or fall equinox. And again, 0 degrees is where direct sunlight hits. Okay, 34. Describe the 3 different Milankovitch cycles. You don't need to memorize the exact names, but you do need to know what changes in each cycle. Now again, you don't even really have to be able to identify which one is which. Just know that there are 3 cycles and be able to describe what those 3 cycles are. First cycle is that the orbit becomes more and less like a circle. There's the sun. More or less like a circle over time. And by the way, I used to always draw it in the middle. I now realize that was a little wrong. When it's in an ellipse like this, it should be down at one end. So this is called eccentricity. You don't have to know that. But basically the orbit becomes more or less circular over tens of thousands of years. The second Milankovitch cycle is that the tilt of the Earth becomes a little bit more and less extreme. This is certainly exaggerated. It only goes by like 2 or 3 degrees. But basically, this tilt is going to go more and less like that. And again, it's over tens of thousands of years. And the third one has to do with the direction that the axis faces. So it's going to kind of wobble like this. So every, 30, 40, 50,000 years, the tilt is going to kind of move like that. And you liken it to like a dreidel spinning or some kind of top where it wobbles, wobbles, wobbles. Okay. 35. Greenhouse effect. Okay, so it starts with the sun shining down on the Earth. So sunlight comes down like this. Sunlight passes right through greenhouse gases, straight through. Some of this sunlight is going to bounce off back into space. And now that we've talked about ice albedo effect, we know that, particularly this is the stuff that hits the ice, flies right back into space. However, a lot of this other sunlight gets absorbed by the Earth and then re-released as heat. And you have to note that there's now a difference between sunlight and heat. So again, we have sunlight here, and we have heat here. Sunlight can pass right through greenhouse gases. Heat cannot. Okay? So while the heat's flowing through the atmosphere, there's all these tons of gases up there. Very few of them are greenhouse gases. O2 does not absorb heat. N2 does not absorb heat. But things like CO2 CH4 and H2O, they do absorb heat. They absorb heat and then they re-release it in different ways, like this. Same thing with H2O. Re-release it in all different ways. And this re-released heat that goes down ends up keeping our planet warm, and it's essential that it were there. Otherwise, Earth would be a giant snowball, but too much of it makes it too hot. 36. Why is it important to distinguish between sunlight and heat? Again, it's because sunlight passes right through greenhouse gases. Heat does not. Heat gets trapped by it. Same thing with glass. Heat passes right through glass. Sunlight passes right through glass. Heat, however, does not. That's why in like October, November, the little space outside Kim's booth is always very warm because it traps heat. That's why your car gets especially hot over the summer. Like even at like 6, 7 o'clock when the sun's gone down, well, when it's starting to go down, all that heat is still trapped in there because it can't escape the glass. 37. Name several key greenhouse gases. The 3 most common ones we talked about are CO2, CH4, which is methane, and water vapor, H2O. 38. Describe the ice albedo feedback cycle. Well, the basic process is this. Sunlight bounces off ice and goes back into space. But when sunlight hits water, it gets absorbed and it gets re-released as heat, which causes things to get warmer. So the feedback starts when let's just say it gets a little bit warmer for whatever reason. It gets a little bit warmer. Well, that's going to cause some ice to melt, which causes less sunlight to bounce back into space, which causes more sunlight to get absorbed and re-released, which makes it get a little bit warmer. Well, and now it's a little warmer, so a little more ice is going to melt, and more sunlight's going to not bounce into space. Less sunlight is going to bounce into space. More heat gets absorbed. It gets warmer, more ice melts, and so on. It's a feedback cycle. It feeds back into itself, and it gets worse and worse. Positive feedback. 39. Photosynthesis. Well, the basic process of photosynthesis is CO2 plus H2O yields, with the help of sunlight, O2 plus sugar for the plants. So basically, every time photosynthesis happens, CO2 is pulled out of the air and turns into sugar and plant material, which is a good thing for us. It also gives us our O2, otherwise we wouldn't be here. So the basic feedback process starts when, for whatever reason, it gets a little bit warmer. Well, when it's warmer, plants thrive a little bit more, and plants grow a little bit more. And the more plants grow, the more photosynthesis happens globally. So again, more photosynthesis means more CO2 pulled out of the air, and that means it gets a little bit colder. So in this case, it got warmer, plants sucked more CO2 out of the air, it now got colder. So nature has corrected the problem, negative feedback cycle. 40. Describe greenhouse gases trapped in ice feedback cycle. Well, greenhouse gases are trapped in ice. CO2, CH4, those two especially. Water vapor really is ice, so that one doesn't really count. So the basic idea is that for whatever reason, it gets a little bit warmer. That causes ice to melt. That causes whatever gases happen to be trapped in that ice to now be released. When they were trapped in ice, they were fine. They weren't doing anything. But now they're in the air. They're causing trouble. They're absorbing heat. They're re-releasing heat back down to Earth. And as a result, it now gets even warmer, which causes even more ice to melt, and so on. The cycle just keeps sort of repeating itself. Okay? Positive feedback cycle. 41. Weathering of rocks. Okay? The basic process you need to know for this, there's a complicated formula. You don't need to know that. All you basically need to know is that CO2 plus rocks yields other kind of rocks. And the idea is CO2 gets pulled out of the air every time this happens. And just for the sake of being thorough, I'll write the actual formula. CO2 plus, oh boy, should I look this up? Silicon. Well, you guys should have it in your notes. I don't have this memorized. But it forms, it forms SiO2 plus CaCO3. So I can maybe piece this together. Silicon carbonate, calcium hydroxide. Well, again, the actual formula is not important. The idea is CO2 gets pulled out of the air, and this process basically causes the Earth to cool down. So the feedback cycle starts when it gets a little warmer for whatever reason. Well, when it gets warmer, that causes more evaporation to occur, so more moisture in the air, and that leads to more rain falling. When rain falls on rocks, this process continues. This is the weathering of rocks. So when there's more water flowing over rocks, this process happens more, which pulls more CO2 out of the air. CO2 being a greenhouse gas is going to be removed from the air, makes it cooler, negative feedback process. 42. Explain how the three types of rocks are formed. Okay, sedimentary rock forms when larger rocks are broken down through weathering, so through rain and wind and sand. They break rocks down into little pieces. Those little pieces travel downstream. They can end up at the bottom of a lake, they can end up at the bottom of an ocean, or the river could dry up and they could end up just sitting there. Well, if they pile up for millions and millions of years, they get this pile of little sediments gets so high that it compresses down into sedimentary rock. So you can't just say that like little pieces of rock just stick together, because they never just do that spontaneously. It needs to be thousands of feet of sediments piling up before it has enough weight to crunch itself together. Second type of rock is igneous. Igneous rock basically forms from magma cooling. So deep inside the earth, rock is getting melted into magma. That magma can either freeze back into rock within the earth over millions and millions of years. And in fact, that's what gives large grained igneous rocks their grains, like granite. If you guys have granite countertops at home, those big chunks in there only form after millions and millions of years, hundreds of millions of years. The other alternative is that magma can get spit out of the earth out of a volcano, and it cools pretty much instantly, and that forms other types of igneous rock. The third type of rock is metamorphic rock. With this, you need some kind of rock to end up deep, deep inside the earth. What happens at a subduction zone, it goes deep down into the earth. Now some of it will melt off and go up, but other parts will continue to go down deeper and deeper. And as it goes deeper and deeper, the intense pressure and temperature inside the earth is going to completely smush all those rocks together. It's going to completely change it on the particle level, and it's going to metamorphose or undergo metamorphosis into a new type of rock, metamorphic rock. 43. Magma from the mantle often gets erupted from volcanoes. Explain how the mantle gets replenished with stuff to erupt. Well, the stuff coming out is magma through volcanoes, and the way it gets back in is through subduction zones. Basically, you have some kind of continental crust like this. You have some kind of ocean crust like this. When they collide together, this one gets pushed underneath. So it ends up traveling down like this. Okay, so basically the process goes like that. And it's very hot and high pressure under here. So this is going to melt into new magma. Okay? And that's how it gets replenished. 44. How does a sedimentary rock turn into an igneous rock? Well, in order for this to happen, the rock needs to end up back inside the earth. So it basically needs to, can't go back, but it needs to ride that conveyor belt down through the subduction zone. Once it gets back into the mantle of the earth, it's going to melt into magma, which can then freeze into more igneous rock. 45. How does sedimentary rock turn into metamorphic rock? Okay, again, what it needs to do is go down into the mantle. So it has to, again, ride that subduction zone down into the earth. And now at this point, it needs to not melt right away. It needs to keep going deeper, where it gets super, super hot and super high pressure. And now it's going to change into metamorphic rock. 46. How do igneous or metamorphic rocks turn into sedimentary rocks? This one's a little more simple. This happens at the surface. It's basically weathering, erosion due to rain and wind, break big rocks into little pieces of rock. Those little pieces travel downstream. They build up and pile up super high, thousands of feet high over millions of years. and the weight compresses them together into sedimentary rock. 47. The pictures below represent particles of matter. Which of these boxes contain mixtures? The mixtures are B and D because they're different particles inside. 48. Which of the boxes contain pure substances? That's going to be A and C because each particle is identical. 49. Of the boxes that contain pure substances, which contain compounds, which contain elements? Well, again, the pure substances are A and C. So A contains compounds and C is just elements. I'm going to stop there.